Okay, now I would like to explain about the Gauss law. So the Gauss law states that the electric flux passing through any closed surface is equals to the total charge enclosed by that surface. Okay, generally the electric flux represented by psi symbol and electric charge represented by Q. So the Gauss law states that psi equals to Q enclosed. Q enclosed. So the electric flux passing through any closed surface is equals to the total charge enclosed by that surface. So it is a Gauss law statement. So for example, so this is one closed surface. Here the charge enclosed by this closed surface equals to Q. So the Gauss law states that the electric flux passing through this closed surface. The electric flux flows like this. The electric flux passing through this closed surface is equals to the charge enclosed by the closed surface. Here the charge enclosed by the closed surface equals to Q and electric flux is represented by psi symbol. So Gauss law statement psi equals to Q enclosed. If charge equals to Q, Q enclosed value equals to Q. If charge equals to Q1, in that case psi equals to Q1. So this one is Q enclosed. So for example, the closed surface enclosed charge value equals to 1 coulomb. In that case the electric flux psi equals to 1 coulomb. Okay, so next one, the mathematical representation of Gauss law. So let a charge Q inside the imaginary closed surface. This is one imaginary closed surface. So now consider a differential surface on this imaginary closed surface. So this is one differential surface. So differential surface area equals to ds. So the flux produced by the charge flows in normal direction. So here the charge produces electric flux in this direction. Okay, in radial direction it produces the electric flux, and it flows in normal direction in this closed surface. So the differential surface area in normal direction ds bar equals to ds into an bar. The differential surface area in normal direction is dsn. Here suffix n is there. dsn bar equals to ds into an bar. Here an bar is normal unit vector. So generally the flux passing through differential surface area ds is the product of the normal component of flux density and differential surface area. In any surface the flux equals to flux density into area of the surface. So here now we have to find the differential electric flux, or the flux passing through this differential surface area. So it is called differential electric flux. The differential electric flux equals to the normal component of electric flux density into this differential surface area. In any case, so to find the electric flux, first we have to find the normal component of electric flux density. Next, by multiplying with surface area, finally we get the electric flux. So here we have to find the flux passing through this differential surface area. So the flux passing through this differential surface area is differential electric flux. The differential electric flux equals to the normal component of electric flux density. Normal component of electric flux density and differential surface area product. So d psi equals to dn into ds. Here dn is normal component of electric flux density and ds is differential surface area. The normal component of flux density equals to dn equals to modulus of d bar into cos theta. So every vector having two components, normal component and tangential component. The normal component equals to the magnitude of the vector into cos theta. The tangential component of any vector equals to magnitude of the vector into sin theta. Here dn is normal component of electric flux density. So the normal component equals to modulus of d bar into cos theta. If you want to find the tangential component equals to modulus of d bar into sin theta. Okay, here dn equals to modulus of d bar into cos theta. So this is the tangential component of electric flux density. So now d psi equals to modulus of d bar into cos theta into ds. So we know that a bar dot b bar. So dot product of the two vector is represented by a bar dot b bar. A bar dot b bar equals to modulus of a bar into modulus of b bar into cos theta. So here modulus of d bar cos theta ds. So it can be written as it equals to d bar dot ds bar. Okay, a bar dot b bar equals to ab cos theta, d bar dot ds bar equals to d into ds into cos theta. So d into ds into cos theta can be written as d bar dot ds bar. D psi equals to d bar dot ds bar. So the total flux equals to psi equals to integral d psi. So by integrating this expression, so finally we get the total flux passing through this closed surface. So psi equals to integral d psi, it equals to integral d bar dot ds bar. Here type of integration, surface integration. Here ds bar is there, so type of integration, surface integration, and we know that this is one closed surface. So here we have to use the closed integration. So it is closed integration d bar dot ds bar. So this integration is closed surface integration. So generally in Gauss law, to find electric field intensity and electric flux density, EFD means electric flux density. Electric flux density, we need to draw a closed imaginary surface around the charge. So this surface is called Gaussian surface. Here this surface is called Gaussian surface. So generally in Gauss law, to find the electric field intensity and electric flux density, so first we have to draw one closed surface around the charge. So this closed surface is called Gaussian surface. Okay. So finally the Gauss law statement, mathematical representation of Gauss law, psi equals to closed surface integral d bar dot ds bar equals to q enclosed. This is enclosed charge value. So for example, if there are number of point charges q1, q2 up to qn enclosed by the closed surface, then the q enclosed or total charge equals to sum of these charges q1 plus q2 up to q suffix n or summation of qn. So here n equals to 1 to n. So psi equals to q or it equals to summation of qn. So for example, okay, this is one imaginary surface. Okay, this is one imaginary surface inside the surface. So for example, three charges are there. First charge q1, q2 and q3. So here by applying Gauss law, we can write the mathematical equation. So psi equals to q1 plus q2 plus q3, q1 plus q2 plus q3. Okay, so this total equals to q enclosed. So Gauss law equals to electric flux passing through this closed surface equals to the charge enclosed by the closed surface. If one charge q1 is present, psi equals to q1. If two charges q1, q2 are present inside the closed surface, psi equals to q1 plus q2. If three charges present, psi equals to q1 plus q2 plus q3. So for example, inside the closed surface, the charge value equals to 10 coulombs. In that case, psi equals to 10 coulombs. So the flux passing through this closed surface equals to the charge enclosed by this closed surface. It is the Gauss law statement. Okay. So psi equals to q, it equals to summation of q suffix n. Here n equals to 1 to n. So for example, type of charge is line charge. In that case, the Gauss law mathematical representation, psi equals to q, it equals to line integral rho l into dl. Here rho l is line charge density rho l. So for surface type of charge, the Gauss law representation, mathematical representation, psi equals to q, it equals to surface integration rho s into ds. Here rho s is the surface charge density. So similarly for volume type of charge, the Gauss law, psi equals to q, it equals to volume integration rho v into dv. Here q is q enclosed all cases. So finally the mathematical representation of Gauss law, okay, this is one formula for point charges, psi equals to closed line integral d bar dot ds bar equals to q enclosed. So for all type of charges, we can use this formula. So next one for line charge, psi equals to q equals to line integral rho l dl. Surface charge, this is the formula, and for volume charge, this is the Gauss law equation. So next Gaussian surface. So Gaussian surface is one imaginary surface. The surface over which the Gauss law applied is called Gaussian surface. So to find the electric field intensity and electric flux density, so we have to draw one closed surface around the charge. So this surface is called next. For this surface, we have to apply Gauss law. The surface over which the Gauss law applied is called Gaussian surface. So the Gauss law the Gaussian surface must satisfy the following conditions. So first one, the Gaussian surface satisfies the following conditions. First one, the surface may be irregular in shape but should be sufficiently large to enclose the entire charge. Okay, this is the first condition. The Gaussian surface may be irregular in shape but should be sufficiently large to enclose the entire charge. So it must be enclose the total charge. So next one, the surface must be closed. Okay, this Gaussian surface must satisfy these two conditions. It is sufficiently large to enclose the entire charge. So next, the surface must be closed surface. So next, applications of Gauss law. So by using Gauss law, first we can find the charge enclosed by the closed surface or the flux passing through the closed surface. So next one, we can find electric flux density. D bar means electric flux density, E bar means electric field intensity due to symmetrical charges. So symmetrical charges means point charge, line charge, surface charge and spherical charges. So we can find the electric flux density and electric field intensity due to these charges. So previously in general method we find the electric field intensity due to point charge, line charge and surface charge and spherical charge. So by using Gauss law, in a simple way we can find the electric field intensity and electric flux density. Okay, so compared to general method, so by applying Gauss law, in few steps we can find the electric field intensity and electric flux density. So next one, Gauss law proof. So let a point charge Q at origin. Okay, this origin, charge Q located at origin. So in Gauss law, first we have to determine the electric flux density d bar. So next, by using d bar E bar relation, we know that d bar equals to epsilon into E bar. D bar equals to epsilon into E bar. So by using that relation, we can find the electric field intensity E bar. In all cases, by using Gauss law, so first we have to find the electric flux density d bar. So next, by using relation E bar equals to d bar by epsilon or d bar equals to epsilon into E bar. By using that relation, we can find the electric field intensity. So applying Gauss law, so first consider a Gaussian surface, and to enclose this charge, draw a Gaussian surface, imaginary surface. So generally for point charges, so select one spherical Gaussian surface. If it is a point charge, our Gaussian surface must be one spherical surface. Okay, this is spherical surface around the charge Q. So for this spherical Gaussian surface, the center is origin. So now consider a differential surface on this spherical Gaussian surface. This is one differential surface. This differential surface area equals to ds. So we know that the charge produces the electric flux in radial direction. In this direction, the charge produces the electric flux lines. So in this direction, the differential surface area normal to r coordinate. Okay. So the differential surface area in normal direction is here, the differential surface area. So here the flux lines are passing in this direction into closed surface. This direction means r coordinate direction. So we know that in spherical coordinate system, the coordinates are r coordinate, theta coordinate and pi coordinate. In this direction, the coordinate is radius coordinate. So here the differential surface area is normal to r coordinate. So the surface ds, the direction is normal to ds is ar bar. So now by applying Gauss law statement psi equals to closed surface integral d bar dot ds bar. So psi equals to, we know that d bar equals to electric flux density formula already we derived. So the electric flux density due to point charge equals to q by 4 pi r square. So closed surface integration ds bar. So ds bar means the spherical surface differential surface area. So surface integration ds bar means total the spherical surface area. Okay. So the spherical surface area formula 4 pi r square. So spherical area formula 4 pi r square. So circle area formula pi r square. Similarly, one spherical case, the area equals to formula 4 pi r square if the radius equals to r. So here d bar equals to q by 4 pi r square and closed surface integration ds bar equals to 4 pi r square. 4 pi r square cancelled and finally psi equals to q. So here Q is the charge enclosed by the closed surface, so it equals to Q enclosed. So the Gauss law, psi equals to Q enclosed. So it means Q coulombs of flux cross the surface if Q coulombs of charge is enclosed by this closed surface. So the flux passing through this closed surface equals to Q if the surface enclosed charge value equals to Q. Okay, this is the Gauss law statement. So next one, Gauss law application. The electric flux density and electric field intensity due to infinite line charge. So already we derived in general method the electric field intensity due to infinite line charge. The formula is E bar equals to rho L by 2 pi epsilon R into A R bar. So now we are deriving the same expression by using the Gauss law. So first to consider the infinite line charge along the z-axis. So assume the line charge density equals to rho suffix L coulombs per meters. Okay, the charge lies along the z-axis from plus infinity to minus infinity, and the charge density equals to rho L coulombs per meters. So now to apply Gauss law, so we have to select one Gaussian surface. So generally for line charge case, so to enclose the line charge, we have to consider cylindrical Gaussian surface. So here this surface is Gaussian surface, cylindrical Gaussian surface. So assume the radius of the cylinder equals to R and length of the cylinder equals to L meters. So now apply Gauss law. So first Gauss law formula, psi equals to Q equals to closed surface integration d bar dot ds bar. Here Q is Q enclosed. So Q enclosed equals to Q, it equals to surface integration d bar dot ds bar. So here cylindrical Gaussian surface we are using, so we are selected cylindrical Gaussian surface. Okay, the cylinder having three surfaces, top surface, next bottom surface and side surface. So divide this integration into three parts. So first one, top surface integration d bar dot ds bar. Okay, this surface integration, top surface integration. So next one, bottom surface integration d bar dot ds bar. So next one, side surface integration d bar dot ds bar. So we are splitting the cylindrical Gaussian surface integration into three parts: top surface integration, bottom surface integration, next side surface integration. So generally this charge produces the electric flux in radial direction. So the line charge, this is line charge. Okay, this is one line charge. Assume this is one line charge. The line charge produces the electric flux lines. So like this, in radial direction it produces the electric flux direction. So this here also this charge, the line charge produces the electric flux lines in this direction, in radial direction. So it means from throughout the charge it produces the electric flux lines in radial directions only. Okay, so in parallel to this charge, it means in this direction, so in this direction and in this direction the electric flux lines equals to 0. It produces the electric flux lines only in radial direction. So like this only the conductor, the charge produces the electric flux lines. So parallel to charge, it means in this direction or in this direction the electric flux lines equals to 0. So it means in top surface integration, in top surface and in bottom surface the electric flux lines equals to 0. So total electric flux lines flows through the side surface only. In top surface and bottom surface the electric flux lines equals to 0. The total flux produced by this line charge flows through only side surface only. So in top surface and bottom surface the electric flux equals to 0. So in top surface and bottom surface the electric flux density equals to 0. If electric flux is there, electric flux density also present. If electric flux equals to 0, automatically the electric flux density equals to 0. Here the flux passing through this top surface and bottom surface of the cylinder equals to 0. So automatically in top surface and bottom surface the electric flux density equals to 0. So finally here three surface integrations are there. In top surface d bar, bottom surface d bar equals to 0. So this first term component equals to 0 and the second term equals to 0. So bottom surface integration d bar dot ds bar equals to top surface integration d bar dot ds bar equals to 0. So this expression becomes q equals to side surface integration d bar dot ds bar. So here the electric flux flows in radial direction. So the electric flux density direction also radial direction. So d bar equals to dr into ar bar. And differential surface area normal to r coordinate formula. So we know that the differential surface area in normal to r coordinate in cylindrical coordinate system r into d pi into dz into ar bar. D bar equals to dr into ar bar, ds bar equals to r into d pi into dz into ar bar. So this is differential surface area normal to r coordinate. So next equation, d bar equals to dr into ar bar, ds bar equals to r into d pi into dz into ar bar. It equals to q. So this is surface integration. So surface integration means double integration. Dr into r, ar bar dot ar bar equals to 1. We know that the dot product of same unity vector equals to unity. So ar bar dot ar bar equals to 1. Dr into r, d pi dz equals to q. Here dr r constant value, take outside of the integration. So first integration with respect to pi, second integration with respect to z. So pi limits. So cylindrical surface, pi lower value equals to 0, maximum value equals to 2 pi. So integration pi equals to 0 to 2 pi, and the length of the cylinder equals to L. So cylinder minimum length equals to 0 and maximum length equals to L. So integral 0 to L dz, it equals to q. So next equation, dr into r, integral d pi equals to pi, limit 0 to 2 pi, integral dz equals to z, limit 0 to L, it equals to q. So now by applying limits, dr into r, 2 pi minus 0, L minus 0 equals to q, or dr into 2 pi rl equals to q, or dr equals to q by 4 pi, q by 2 pi rl, or dr equals to rho L by 2 pi r. So charge by length equals to charge density. Okay, charge equals to, generally charge q equals to, if it is a line charge, q equals to rho L into L. If it is a differential charge, dq equals to rho L into dl. So q equals to rho L into L. Rho L is line charge density, L equals to length of the charge. Here q by L. So q by L equals to rho L. So dr equals to rho L by 2 pi r. So d bar equals to, here the electric flux direction only in radial direction. So electric flux density also in radial direction. It having only radial component. So d bar equals to dr into ar bar. Dr equals to rho L by 2 pi r. Rho L by 2 pi r into ar bar coulombs per meter square. Okay, this is the electric flux density expression. So next, by using the relation between E bar and D bar, we can find the electric field intensity. Electric field intensity E bar equals to D bar by epsilon. D bar equals to rho L by 2 pi r by epsilon. So finally E bar equals to rho L by 2 pi epsilon r into AR bar. AR bar units are volts per meters. So by using Gauss law, we can find the electric field intensity and electric flux density. So to apply Gauss law, so first we have to select Gaussian surface. So next, by applying Gauss law to this Gaussian surface, we can find the electric flux density. Next, by using electric field intensity and electric flux density relation, we can find the electric field intensity. Here we have selected cylindrical Gaussian surface. The cylinder having three surfaces: top surface, bottom surface and side surface. The conductor or the charge, the line charge produces the flux in radial direction only. So only inside surface only the electric flux flowing. In top surface and bottom surface, the electric flux equals to 0. So in top surface integration, bottom surface integration, values becomes 0. Only side surface integration only present. So next, by solving this expression, finally we get the electric flux density and electric field intensity.